Nature of waves. The first kind of wave we are going to study is transverse wave. What is a transverse wave? A transverse wave is the wave with the vibration of the particle always perpendicular to the direction of the wave travel. Just like this diagram, you see we have a wave here, and the vibration of each particles on the wave is moving up and down, and the direction of the wave is traveling to the right. Okay? In this case, the vibration of the particle is always perpendicular to the direction of the wave travel. This kind of wave is called transverse wave. Examples of transverse wave are water wave, electromagnetic wave, and wave in a string. Let's see how to demonstrate water wave is transverse wave in nature by using the apparatus. First is a clock and the other is a dot vibrator. First, let's put the clock and the dot vibrator on the water. And then we switch on the vibrator. When the vibrators vibrate, a water wave is traveling in the water. When the water wave reaches the clock, you will see the clock move up and down repeatedly. In this case, we see the water wave traveling to the right, which is perpendicular to the vibration of the water particle in the water. Therefore, this kind of wave is called transverse wave. Let's see the physical quantities used to describe a transverse wave. Consider a transverse wave generated by a vibrator connected to a signal generator, as shown in the diagram. Equilibrium positions is the position of all the particles on the string before a wave is set up. Therefore, this line is called equilibrium position. Waveform, or we say wave train, represents the shape of the wave at a certain instant. In this case, this is the waveform, or we say wave train. Displacement is the distance between the particle and the equilibrium position. For example, for a particle P, the displacement of particle P is the distance between P and the equilibrium position. If displacement is y, we say y. Crest is the maximum displacement. In this diagram, this is the maximum displacement. This is the maximum displacement. Therefore, we have this point is called crest. Q is a crest, or B is also a crest. D is also a crest. Trough represents lower displacements of the particle. In this case, R, Y, Z are the points at the lowest displacement. Therefore, we call R, Y, and Z troughs. Amplitude A is the maximum distance of the particle from the equilibrium position. In this graph, we say this is A, this is A, this is also A. The unit of amplitude is cm or meter. And period T is the time for the vibrator to oscillate once. This is also the time for the particle to make one oscillation. The unit of period T is second or sometimes millisecond. Frequency F is the number of oscillation making by the vibrator in 1 second time, or is equal to the number of oscillations making by the particle in 1 second's time. And the unit of frequency is per second, or we say hertz. If we say the period is equal to 2 seconds, which means that the particle or the vibrator needs a time of 2 seconds to make one oscillation. If we say the frequency is equal to 10 Hz, that means in 1 second's time, the particle or the vibrator makes altogether 10 complete oscillations. Wavelength lambda is the distance between two successive points that are vibrating in phase, or wavelength is the distance of one complete wave. In the diagram, we have the wavelength is the distance of one complete length, which is this one, lambda. Or we say lambda is the distance between one complete wave. This is also called lambda. And the unit of wavelength is cm or meter. The last one is wave speed. Wave speed is the distance traveled by the wave in 1 second. That is v equal to d over t. When the source making one oscillation, we have one complete wave produced. In 1 second, there are altogether f oscillations. Therefore, the wave travels a distance of f times lambda, which is the product of frequency and wavelength. Therefore, the wave speed can be written as equal to frequency times wavelength. The instantaneous motion 瞬時間嘅運動 of particles in a traveling transverse wave. When the hand oscillates, a transverse wave is produced and is traveling to the right. At this time instance, what is the instantaneous motion of the particle on the wave? For example, what is the instantaneous motion of this particle, this particle, this particle, and this particle? If the waveform at this time instance is this one, Since the wave is traveling to the right, at a later time t plus delta t, the waveform becomes this one. By comparing the waveforms, we see that the particle between PQ at the instant t, they are moving upward. While the particles between Q, R at the instant t, they are moving downward. Since P, R are the crests and Q are toes, therefore particles at P, Q, and R are instantaneous at rest at this moment. As a conclusion, for a wave traveling to the right, if the wave is a transverse wave, then the particle with positive slope are moving downward. While the particles at the negative slope are moving upward. And the particles at the position of the crust or the toe are instantaneous at rest, or we say stationary. What if the wave is now traveling to the left? Again, we show the wave at a certain time instant t, and the wave is traveling to the left after a time instance t plus delta t. The waveform becomes this one. From the waveforms, we say that the particles between x and y at time t are moving upward, while the particles between y, z at time t are moving downward. Also, since y is a crest and y, x, and z are toes, therefore x, y, and z are instantaneous at rest at time t, or we say they are stationary. As a conclusion, for a transverse wave traveling to the left, the particles with negative slope are moving downward, and the particles with positive slopes are moving upward, which is the opposite of a wave traveling to the right. Again, at the position of crest or choke, the particles are instantaneous at rest.